Hi everyone! In this video, we'll be discussing the Taylor and MaClaurin series and some of their applications. But before we jump straight into the math, let's discuss the basic premise of a Taylor and MaClaurin series. A MaClaurin series is a type of Taylor series, which is a type of power series, which is a type of geometric series. Our good friend Matei shows all the formulas for better understanding. As the video progresses, Matei will be helping us make this topic easier to understand. A Taylor series is a specific kind of power series. So, as a refresher, let's briefly go over the qualities of a power series. A power series is a series that may be written in this form. We have a constant c, which we call the coefficient of the series. And then the variable x. A power series is a bit different from the other series we've encountered because each term has a variable to a power. Before, we only dealt with numbers, but now each term has the variable x. Keep in mind, because x is a variable, we can choose values for x which will cause the series to either converge or diverge. Recall that the sum of a power series can be rewritten as a function of infinite sums. A sigma notation just means to sum up. If a sigma is just summing infinite terms, then we can also write a power series like this. This function represents the sum of a power series like this. Note that this almost looks like a polynomial, except it's infinite, as you can see here. This might not seem important right now, but when we get to the Taylor and MaClaurin series, it'll help to understand how closely related a power series can be to a function. Now, let's briefly recall why power series are important. A power series is very important when it comes to representing functions in a different manner. For instance, take e to the x as a function. If we try to find any of its exact values after inputting any number for x, such as 2, that would be very difficult to do. However, if we represent e to the x as a power series, we're able to calculate its exact value through partial sums within a certain interval of x. So it will look like this. We'll go into more detail on how we got to this conclusion in a bit. If we take this to a graph, you can see that as we add on more values, the graph of the power series we build grows closer to look more like the graph of e to the x. However, we still can't forget about our interval of convergence, because once we go past our interval of convergence, the graph of the power series mismatches and is no longer accurate in depicting the exact values of e to the x. Okay, now to the main topic of this video. So what does a series with a fancier name than the power series have to do with the actual power series? Well, the Taylor series makes up for what the power series lacks. In 11.9, we began to view power series as representations of functions. Remember how we manipulated different equations to fit the form 1 over 1 minus x so we could generate power series based on the form x to the n? Matei put an example of this, so feel free to pause. Well, not every function is going to be able to fit into that form 1 over 1 minus x. There are many functions such as sine x and cosine x that can't be easily manipulated into this form. So how do we come up with a power series that represents functions more generally? The answer is Taylor series. Let's start by taking a look at a general function f of x, which has the power series representation about x equals a. This is the general form of a power series. If we were to plug in x equals a to the equation, it would automatically simplify to the first coefficient c. Let's see what that looks like. We're going to evaluate everything at x equals a. So okay, so you can see how all the terms except for the first are 0, and there are no other x values that we can plug in to find other coefficients. But we can take the derivative of this function and plug in x equals a. So now let's try differentiating the original general power series term by term, making certain to do the power rule for each term. We'll get something that looks like this. Let's do the same thing we did with the original function and evaluate f prime of a at x equals a. Well, all the x minus a's are going to go to 0, which simply leaves the coefficient multiplied by 1. Let's do this again with its second and third derivative. Okay, so now let's do it with its fourth derivative. In its second derivative, the series simplifies to 2c, while in its third derivative, the series simplifies to 2 times 3c. And for the fourth, it simplifies to 2 times 3 times 4c. Matei, what kind of pattern is emerging? That's right, it's a factorial. So I can also write it like this. We can generalize this pattern by writing this. This stands for the degree. What's more is that by solving for c, we can use this to come up with an expression for all coefficients within the power series. When we take the resulting constant involving the nth derivative and plug it back into the power series equation, we result in a Taylor series function. So that's Taylor series checked off the list. What's next? Alright, the MaClaurin series. Despite its scary name, the MaClaurin series is not as bad as you'd think. The MaClaurin series is a very common type of Taylor series where we take the Taylor series function and set a equal to 0. Here's an example of finding the MaClaurin series of e to the x by setting a equals 0. Again, feel free to pause and observe. So why is the Taylor series important? Well, remember how the power series showed us a way to represent functions outside of their function forms such as e to the x? Taylor series does this too. Some functions are incredibly complex, and by making a Taylor series representation for a function, we split it into polynomial parts. These polynomial terms are comparatively easier to evaluate when we're approximating a complex function. So, this is our Taylor series formula. The MaClaurin series is pretty much the same. It's just a Taylor series when a is equal to 0. So, that formula will look like this. Approximation of functions is an incredibly important, if not the most important, application of the Taylor series. Let's take a general form of the Taylor series. We have this string of polynomial terms from n equals 0 to n equals n. For each degree of n, from 0 to whatever number you want, there's a corresponding polynomial term. Okay, so now the notation Tn of x is called the nth degree Taylor polynomial of f at a. It sounds confusing, but trust me, it's not as bad as it sounds. Tn of x simply represents the polynomial expressions that can be made from a Taylor series. You see, when it comes to approximating a function through a Taylor series, the more terms we add to Tn of x, the more accurate the sum becomes to the function itself. Therefore, when we say nth degree Taylor polynomial, it can be translated as we add n amount of terms to Tn of x. The higher the nth value, the more accurate the approximation to the function is. So, for example, relating back to the e to the x that we showed earlier, if we were told to find its partial sum if n is from 0 to 3, we will get this. We know this based on the example Matei brought out earlier in the video. But if n is 0 to 5, the partial sum extends to this. Which becomes more accurate to e to the x's exact graph. Therefore, the partial sum becomes more accurate only within a certain interval. Which becomes more accurate to e to the x's exact graph. Therefore, the partial sum becomes more accurate only within a certain interval.
All right, well, let's now come up with a more mathematical understanding for this. How would we describe this using mathematical notation? Well, let's try taking the limit of Tn of x as n goes to infinity. Based off of what we just said, this should equal the original function f of x. This is our mathematical notation or understanding for this concept. This means that as the nth term, quote unquote, grows, and we add more terms of the series, the sum of the series will resemble the original function. So for instance, the limit of the Taylor series for e of x as n goes to infinity matches the exact value of e of x for whatever number is plugged in for x. Taking a look at this graph, we can see that as n increases, the approximation for the function becomes more accurate. But t and x isn't a perfect representation of f of x most of the time. It's an approximation. So how do we account for the remainder? Well, we come up with this thing called Rn of x. Rn of x is the original function minus the approximation. And it gives us the remainder. Now we can also rewrite this such that the original function is equal to the remainder plus the approximation. If we take the limit of Tn of x as n goes to infinity, it's the same as taking the limit as n goes to infinity of f of x minus Rn of x, according to what we found above. This guy right here. Now, the limit of this section right here as n goes to infinity is the same as taking the limit of each of these terms, the limit as n approaches infinity of f of x minus the limit as n approaches infinity of Rn of x. The limit as n approaches infinity of f of x is going to simply be f of x, because there is no n in the function. Whereas, if the limit of Rn of x as n approaches infinity is equal to 0, this is going to equal 0. And therefore, you have the limit as n approaches infinity of Tn of x is simply equal to f of x. And this shows what we already know, is that if the remainder is equal to 0 or goes to 0, then when you take the limit of Tn of x as n approaches infinity, it's going to become a perfect representation of the function f of x. Now, another theorem we'll need in approximating functions by Taylor series and nth partial sums is Taylor's inequality. Let's throw up a theorem. Now, what this theorem says is that if we have a function which we choose to represent as a Taylor polynomial, we're also going to have this little remainder. And we're saying that on an interval, if it is the case that the limit of the remainder as n approaches infinity is equal to 0 on that interval, then, assuming that Tn is the nth degree Taylor polynomial of the function at a, it is the case that the function itself is going to be equal to Tn of x on that interval. Now, basically, to restate what I just said, we have here an interval where x minus a, that absolute value, is going to be less than some number r. It's basically just saying we have this radius or interval where on that interval, the function is going to be able to be represented by the Taylor polynomial. And this is important because one of the most important applications of Taylor polynomials is approximating functions. Now, another theorem we're going to need in approximating functions by Taylor series and nth partial sums is this tricky theorem called Taylor's inequality. And it's more of an inequality than a theorem. And I'm going to write that coming up right now. Taylor's inequality states that if we have a function and we take the derivative, that's what this refers to, of that function, and if we take the absolute value of it such that it's less than or equal to m on an interval where x is just hanging out on that interval and is less than or equal to d, then the remainder, which is Rn of x, then the remainder Rn of x of the Taylor series must satisfy or satisfies the inequality, Taylor's inequality, that looks like this. And what I'm about to write is ugly. It's the absolute value of the remainder, which is going to be less than or equal to a number which is greater than the next derivative over n plus 1 factorial multiplied by x minus a n plus 1. This is an exponent right here. This is not a derivative for reference. This is an exponent. On the interval, x minus a is less than or equal to d. Now, this is a lot of writing, right, McTay? Yeah. Well, we'll try and make it as simple and easy to understand as possible. Taylor's inequality helps us find the values Rn of x, aka the remaining sum of the terms, aka the remainder, this guy right here, not included in the nth partial sum, Tn of x. To say that again, the reason why we care about Taylor's inequality is that if we can find the value of Rn of x to be small on an interval, x minus a is less than or equal to d, if we can make Rn of x small, or know how large Rn of x is, then we also know how accurate Tn of x is. The smaller Rn of x is, the more accurate Tn of x is. And that means that the polynomial expression we get, right, Tn of x, is going to be more accurate to the function that we're trying to approximate. This is really just a way to understand how accurate our function really is when we approximate it.